So welcome to PH 101 lab. This is our experimental demonstration part of our third experiment, ballistic pendulum. So let's understand the apparatus used to calculate the muzzle velocity and what we have discussed in part 1. So we know that we have discussed this in our experiment. This is the locking stick used to lock the ball. This is actually the projectile launcher. As you can see, there are 3 ranges. It is a plumb bob which should be at 0 degrees. This is the release string when we lock the ball, which we will be doing shortly. This is actually the pendulum. This is actually the pendulum, and it can oscillate back and forth. So you can see. Here you can see it's the pendulum. Here we have the catcher, and inside the catcher we have a ball. So if you want to release the ball, you have to push it. So this is actually the ball. Now this is the catcher. This is the catcher. It is the ball bearing. Here we have the degree scale, and this you can see this black pointer is called the angle of deflection indicator. So actually it is connected with this pendulum. So if it moves, the angle of deflection indicator will move also. So actually it tells you the angular displacement of the projectile. So this is actually the angle of deflection indicator. So keep in mind, this is the initial setup. So what you have to do is, if you want to lock the ball at long range, and then you will pull this thread towards yourself, and the ball will leave the barrel with a muzzle velocity. Now as it leaves the barrel, it will strike this catcher, and it has a hole here. The catcher will catch the ball, and then it will move with some velocity. So as it moves, as you can see that the angle of deflection indicator also moves. So let's say it moves a little high. It was the initial position here, it was here at the mean position. At the instant we pull the thread, after locking the ball, it will move with certain velocity. Covering some angular displacement, here from here we will calculate our theta. Let's say it moves here. Now it will come back definitely. So you can clearly see that the angle is here. The angle here is 27.5 degrees. So by looking onto this degree scale, the angle of deflection indicator will tell you the value of theta, which we will need for our height calculation. H is equal to RC 1 minus cos of theta. So we will get theta from here, and then we will calculate the height, which will be our H1. So we have to do it for 4 trials. Now the second thing is how to lock the ball. We will move this pendulum with the catcher above, and we will lock it, or we will place it here, right, like this. So initially what we have to do is to place the ball in the barrel of the projectile launcher. So this is our ball. So it has a mass of mb. So its mass will be mb. So you can calculate its mass from the spring by using a balance. So you can calculate its mass. Now what we have to do, we have to place the ball here, right? So first you have to lock the ball using this stick. So we will lock the ball, let's say at the medium range first. I have locked the ball. So you have to lock the ball at the medium range. Now you will have to move this pendulum back to its original position. Now you have to take care of 2 things. The first thing is, this angle of deflection indicator should be initially at 0 degrees. Right, you can see it is exactly at 0 degrees. So you have to keep in mind. Now the second thing is, this is very important. Now after locking the ball, when I will pull this thread, the ball will leave this projectile launcher, and as it leaves, it will have a muzzle velocity. At the instant it strikes the catcher, it will stuck inside the catcher, and then the catcher, which is the part of this pendulum, will move, covering some distance, angular displacement from here, theta. So you will note down the theta. Let's say it's 25 degrees. So what I am trying to say is, when the ball is stuck inside the catcher, then the mass of the catcher will be mb plus mc, and it will be moving with velocity v, not v naught. V is the velocity after the collision, which we have already discussed. Now let's fire the ball. What happened? So you can see that as I fired the ball is now stuck inside the catcher. The catcher has caged the ball, as you can see, and from here you can see that the angle of deflection has moved a distance of angular displacement of the angle is 33 degrees. The angle is 33 degrees. So this is your theta 1. You have to note it down. Now for the second case, you will again release the ball using this pin. As you push it, the ball will come out, as you can see. Now you will again keep it straight, right? You will place the ball here, right? You will lock it at the medium or at the, so if the mass of the ball is more, you will have to lock the ball at, let's say, at medium range. And if it's not working for the medium range, let's say the angle is very small, then you can lock the ball at long range. So let's say I'm locking the ball again at medium range. I'm not using the long range. After locking the ball, we will again move this pendulum back to its initial position, and the pointer should be again, here we have the deflection indicator or the pointer which tells us the angle of deflection theta. So again you will have to place it at 0 degrees. When I will fire the ball, again by pulling the thread, again the catcher will catch the ball, and in the angle of deflection from here we have to note it down, it's now 40 degrees. The angle is now 40 degrees. So our theta 2 will be 40 degrees. Now you have to repeat this experiment 4 times. Then you will calculate theta 1, theta 2, theta 3 by looking onto the degree scale. After calculating theta 1, theta 2 and theta 3, you will get 4 heights, h1, h2, h3. When the pendulum moves from here to here, you will calculate this height, which we have already discussed. Now we will take the average, and then we will get the value of h, which we will be discussing shortly again. So this is the way how to calculate the value of h. Now initially there are 2 parts of this experiment. So the first part of this experiment is to calculate the initial velocity of this ball as it leaves the barrel. So the initial velocity, we will call it the muzzle velocity, part 1 velocity. And for the second experiment, for the first experiment, you will keep this pendulum here. There is no need to use this for the first part. So the first part is exactly the same as we did it in our experiment number 1. What you have to do is, we will keep a white paper here, right here. It is similar to the first experiment, so you can check it out. First we have to keep a white paper right in front of the projectile launcher, and the distance from this plus position to the edge of the paper can be calculated using this meter stick. So I will keep this meter stick here, and I will calculate from this plus position to the edge of the paper. So this will be our x dash, which we have already discussed. Now the second thing will be, I will then keep a carbon paper on the top of our white paper right here. Then I will lock the ball at medium range or at short range. Let's say I am locking the ball at medium range, and then I will pull this thread again, and we have to record 10 trials. And after recording 10 trials, we will get distances, we will get dots here by removing this carbon paper. So right here I have a dot now. Now what you have to do is to calculate this distance of this dot from the edge of the paper. So this will be our x1. For the second trial, we will get x2, x3, x4. You have to take the average of all these recorded values. So we will get the x average. Then you have to add this x average with this fixed horizontal distance, and we will get the total horizontal distance from this plus position to the last dot. Now using this x, I know the position of this launcher. So the position of this launcher from the surface of the table is, let's say, it's about 7.5 centimeter. So this is our vertical distance to this plus position from the floor of the table to this plus to the point of launch of the ball. So I will get the value of y from here. T is equal to under root 2y by g. Using this relation, I can calculate the time of flight. So I have calculated this x total distance. I will divide this total distance divide by the time of flight. I will get the initial velocity of this ball, which is our muzzle velocity, and this is our part 1 muzzle velocity. So in the first case, you have just to repeat the first experiment. Now let's move to the second part. In the second part, what you have to do is to lock the ball. Let's say I am locking the ball. For the second case, we have to use this ballistic pendulum. We have to use this setup. So this setup, including this, is the ballistic pendulum. We will keep this ball here in the barrel, and then we will lock it using the locking stick, like this, right? So you will lock the ball at medium range. Now, what we have to do is, you can remove the white paper. There is no need to use this now. In the second part, you will pull this pendulum with the catcher to its initial position. Now, the next step is to move this angle of deflection indicator to 0 degrees. Now, we will fire the ball, right? You will have to just pull this thread, and as you pull this, what happens? The ball leaves the barrel, it strikes the catcher. So here comes the collision. It's inelastic collision. And what will happen? If you see again, let me repeat. Let's lock it, right? Let's lock it. Now pull this thread again. What will happen? The pendulum will move. It will oscillate, right? We have discussed this. And it will catch the ball. Its mass after collision will be mb plus including the mass of the ball. Initially, the mass of the ball was mb. And after its mass will be mb plus mc. Its velocity initially was v naught before the collision. After the collision, its velocity as the catcher moves with the pendulum, its velocity will be mb plus mc into v. V is the velocity of the catcher after the collision. Keep in mind. So when I will pull this thread, as you can see, it moves. And this angle of deflection indicator will tell you the angle theta. So you have to repeat this experiment 4 times. Then you will put the value of theta into h is equal to rc 1 minus cos of theta. So what is rc? rc is the distance of this pendulum from this position, from the top fixed position to the center of mass of the catcher. So the center of mass of this catcher is here. Keep in mind, right in the middle. Its center of mass, the distance from here to here is rc. Distance from this fixed position of this pendulum to this center of mass is rc. So how to calculate this? Keep this at the center of mass of the catcher, and the distance is about 29.5 centimeter from the center of mass of the catcher to this fixed position, it's rc, and its value is, here its value is 29.5 centimeter. Now the next thing is rb, the distance from this center of mass, the distance from this fixed position to the center of mass of the ball. So the ball is a little down. The ball is at the bottom of the catcher. So the value of rc and rb will be slightly different. So the center of mass of the ball is right a little below the center of mass of the catcher. So I will keep the meter rod here from the center of mass of the ball here, and its value is now, it's now 35. Its value is 30.5 centimeter. The value of rb is 30.5 centimeter. rb is the distance from this fixed position to the center of mass of the ball. Keep in mind. And rc is the distance to the center of mass of the catcher. So it's clear. You have to repeat 4 trials. And what to do next, I will explain this on the whiteboard. Now, after understanding the ballistic pendulum experimentally, as we have discussed on our workstation, there are 2 parts of calculations. So actually this is our experimental demonstration, and this data can be extracted from our experimental observation. So there are 2 parts of this experiment. In the first part, which is the muzzle velocity calculation, and we call it the part 1, V naught. And the second part is the ballistic pendulum, in which we will involve the collision, in which we fire the ball which strikes the catcher, and it imparts a velocity V to the catcher. So there are 2 parts. So the first part is exactly the same as we have calculated the initial velocity of the ball in our very first experiment. So actually in the first experiment we will not be using the ballistic pendulum. We will place the pendulum above. We will lock it. We will move the pendulum above and we will lock it there. In the first part we will not be using the pendulum. We will be just using, or you can say that we will be just repeating our experiment number 1. So we already discussed this in our experiment number 1. We have to take certain trials. We will lock the ball. As we did it, we locked the ball and then we took trials, the horizontal distance x1, x2, x3. x1 is the distance of the first dot from the edge of the paper, x2 is the distance of the second dot from the edge of the paper, and then we have to take trials as we did it, and then we will take the average xavg. So this is the average of the dots or the distance from the edge of the paper. So it's the average distance. Now we will add this distance with the x dash. So x dash as we did it is the fixed horizontal distance from the plus symbol to the edge of the paper. So we know that this x dash, x average, and time of flight can be calculated by 2y by g. Y is the max vertical height as we discussed. So from here we will get the time of flight and we will put this value here. So x plus x average is equal to x, and time period we can calculate easily. So we will get v naught. So in the first experiment we were calling this velocity to be the initial velocity of the ball. So actually it is the muzzle velocity. So this will be our first part, muzzle velocity part 1. It will be our first part. Now the second part involves the ballistic pendulum. Now in the second part, when the ball collides with the pendulum, when the ball collides with the catcher and it is stuck inside the catcher, then what will be the case? So we already calculated this relation h is equal to rc1 minus cos of theta, and we have to fill some tables. So this is table 1 and this is our second table. Now keep in mind v is equal to under root 2gh. We have already calculated. I am not going into the details. You can check the first part of this lecture. So it is the velocity after the collision. V naught is equal to x by t is the part 1 muzzle velocity. It should be noted that it is muzzle velocity calculated from part 1. Keep in mind, this is the muzzle velocity. We have derived this relation. V naught is equal to md plus mc mb under root 2gh. So this is actually the calculated muzzle velocity. mb is the mass of the ball, which is 61.28 grams. mc is the mass of the catcher, which catches the ball, is 235 grams. So you are now clear about these things. So rc is the length of the pendulum to the center of mass of the catcher, and rb, as we have calculated, is the length of the pendulum up to the center of mass of the ball. So first you need to calculate these things as we did it. Now what we will do, we will first find 4 trials. We will, in order to fill table 1, you need 2 things. The first one is to note theta down from the degree scale. So when you note theta down, you will get h1. And how you will get h1, and this h1 can be calculated from theta 1. Let's say this is 25 degrees. So you will put here 25 degrees. RC we have already calculated. You will get the h value. So if this is first, so it will be h1. Let's say it is 1.5 centimeter. And your theta was, let's say, 25 degree, as we have discussed. So it depends on your calculations and your observations. So theta 2 will be some other value, theta 3 will be some other value. So you will be doing it for the short range. You can do it for the short range, for the long range, as well as for the medium range. So if you want to do it, you should do it for the long range. So then we will calculate h2, theta 2 for the second trial. Theta 2, we will place this theta 2, so it will become theta 2. RC is fixed, we have calculated it. We will get h2. In the second case, we will get h2. Then in the third case, we will put theta 3 here. We will get h3. Then in the fourth case, we will get h4 from theta 4. And this is calculated from this right angle triangle, which we have already discussed in our previous lecture. So these are the prerequisites. So where h is equal to h average. So we will take the average of these heights by dividing by the number of trials. So there are 4 trials, we will divide it by 4. We will get a single h. So actually this h represents an average value. Keep in mind, this h represents the average value. Now this is very simple to calculate. Now what is the average height? Just very simple. you have 2gh. You will get the average value of h from here, put it here. So you will get the velocity after the collision. So you will write the value here. Now in the second case, the muzzle velocity V0 part 1. So it is the velocity you have calculated from the part 1, just like you did it in the experiment number 1. And it is the velocity V0 is the velocity, the muzzle velocity, which we have calculated using law of conservation of momentum. So we have derived this equation, don't worry, you can go and check the first part of this lecture. So this is the calculated muzzle velocity. So you have the mass of the ball, you have the mass of the catcher, and this is the height, the average value. So you just need to plug the values and you will get the calculated muzzle velocity. Now you will put the calculated muzzle velocity here. Now what is the velocity after the collision? You have calculated the velocity after the collision using this relation, and average height is, you have calculated the average height from here. So you have filled this table. Now what is this percentage difference? This percentage difference is actually the difference between the muzzle velocity and the muzzle velocity. Sorry, this is the difference between, percentage difference is calculated between the muzzle velocity and the calculated muzzle velocity. So it's very simple. Let's say this is the muzzle velocity from part 1 is 3.9. and the calculated muzzle velocity is 3.6. So you need to, so it will be 3.9 minus 3.6 divided by 3.9 multiplied with 100%. So you will get the percentage error. Definitely we calculate the muzzle velocity using this formula for the comparison purposes. For example, you want to check the muzzle velocity from part 1 and the calculated muzzle velocity. So what is the difference between, the percentage difference between these two velocities? So it will be something less than, it should be less than 10 at least, or it should be less than 5 for this case. Now when you calculate the difference, there are some other things you need to know. The first thing is the time period of this pendulum is, we tell the students that its time period is 1.096 seconds. So you can also calculate this value if you want to using this time period relation, 2 pi by under root RC. RC is the length of the pendulum to the center of mass of the catcher as we have calculated, and G is the gravitational acceleration. So if you put this value, you will get this value. So you can either plug this value directly, or you can calculate using the time period relation. And you have to calculate the loss in the kinetic energy. So the loss in the kinetic energy is kinetic energy before collision, that is the initial kinetic energy, minus kinetic energy after the collision, that is the final kinetic energy, dividing by the kinetic energy initial, absolute, and multiplied with 100%. So how to do it? We have discussed this in our previous lecture. So I will briefly explain it simply, that for the kinetic energy initial, it will be, it's because before the collision. So before the collision, the ball is not inside the catcher. So the velocity will be half mass of the ball mv, and it's having the muzzle velocity, so v square. So you will get the kinetic energy initial from here. Now the kinetic energy after the collision, which I am calling the k dot e f in the subscript, is equal to half. Now after the collision, the ball is stuck inside the catcher and it's moving with the catcher. So we will take both the masses, mass of the ball as well as the mass of the catcher. So we will get mb plus mc, and now it's moving with v, the velocity after the collision. So we will put here v. So now you have the table. You will just use these values in this equation. And when you have calculated the kinetic energy initial and the kinetic energy final, you can easily calculate the percentage loss in the kinetic energy. So this is very simple. Now by involving some rotational factors, by involving some rotational quantities, for example inertia, angular frequency, because the pendulum is oscillating, so we have the angular displacement, so we can introduce angular quantities. So we have calculated this relation again. So I have written it directly in experimental demonstration. V0 is equal to 1 over mv rb. You know these values too. It is inertia, and mb plus mc into gh. mb plus mc into gh. So where I is equal to mb plus mcg rcm, which is, you can call it rcm or rc, t square is the time period, 4 pi square. I have derived this equation as well as this equation in the first part. So from here you will calculate the I, you will plug this value here. The time period can be either plugged directly, which is 1.096, or you can calculate this time period from here. So you will put it here. Now from here you will calculate the inertia, and the value of the inertia you can put it here. So we will get the muzzle velocity. Now what is the muzzle? It's actually the exact value. It's actually the exact value. This is actually the exact value of the muzzle velocity. Using this equation, it's the exact value. And using this method, V naught is equal to mb plus mc under root 2gh. It's actually the calculated method or the approximate method. We have discussed this in our previous part 1 theory and calculations part. So this is all about this experiment. It's not very difficult. It seems to be difficult, but it's not very difficult. You have to understand the prerequisites and the basic idea how to perform this experiment. So hope so you understand now what is ballistic pendulum and how linear momentum is used to find these quantities, the muzzle velocity, and how kinetic energy is not conserved. You have now the basic understanding of the elastic collision, inelastic collision, and more importantly, you know the purpose of this experiment. So the purpose of this experiment was to calculate the muzzle velocity using the conservation of momentum. Thank you.